Hello, welcome back to another video where today we will be using Cardano's formula to write a Python function to calculate the specific values given it at a specific pressure, temperature for the SRK equation of state. Okay, simple enough, right? So the first order of business is using Cardano's formula. So we'll want some kind of function to utilize Cardano's formula, right? And for a quick reminder, a Cardano's formula is essentially quadratic equation for a third power polynomial, where quadratic equation finds the roots for a second order polynomial. A Cardano's formula does it for a third power polynomial. And I am just pulling up excuse me, my reference material for this, because I can't remember all of it in my head, right? So remember last time we used all this stuff up here for the cubic equation state. Today we are, look at this, for a cubic equation, it's saying that Q is equivalent to that expression and R is equivalent to that expression and theta is equivalent to that. So, and remember that we need to separate between our two functions, that A and B and C, they're not the constants, they're the coefficients of the cubic equation, of a of a generic cubic polynomial. Okay? So, let's go ahead and tackle this. Looks like the first thing we might want to compute is theta, right? So, let's see what happens. So, define, we'll call this cube underscore roots. And what is it taking in? Well, it is taking in the coefficients A, B, and C, right? A, B, C. Okay? And the first thing is that we want to compute Q. So Q is equal to A squared minus 3B over 9. And R is equal to 2 times A squared, cubed, minus 9 times A times B plus 27 times C, all over 54. Great. Now we can calculate theta. Theta is equal to 2 NP dot R cosine of R divided by Q to the square root of Q cubed is raised to the power 3 over 2. Yes. Okay. Well, knowing that, it's saying Q and R are real, and when R squared is less than Q cubed, then the cubic equation has 3 real roots. Find them by computing so and so. So, sounds like we're setting up a if-then statement. So if Q R squared is less than Q cubed, then X roots, we'll do roots. Roots equals, or actually at this point we can just return. Or let me think. Let's not do that. Roots equals, and we'll make it an array, and then we'll use NP sort to put them in order from lowest to highest. Okay, so x1 is equal to -2 times Q to the 1/2. It just struck me that I'd probably want to make sure that this is in parentheses for it to compute correctly, times NP dot cosine theta over 3 minus A over 3. Let's make sure that's in parentheses. Again, I was saying to myself that I want this to be an array. There we go. Otherwise, x2 is -2 times q to the 1/2 times np dot cosine theta plus 2 times np dot pi. This should be in parentheses. All over 3 minus a over 3. Okay. And finally, the last expression, -2 times, you know, at this point, I should probably just copy paste. No need to handwrite everything. Times np dot cosine. This time it is theta minus 2 times np pi all over 3 minus a over 3. Okay. Where did my square bracket go? It disappeared. I hope that I'm not missing anything. Unexpected indent. There it is. That's where it disappeared to. Okay. Let's make sure that, yep, parentheses match up. Perfect. Okay. And then after this, we'll want to, apologies. That's the right indentation. Return np dot sort roots. Okay. Else. So if r squared is not less than q cubed, it says otherwise compute this, where the sign of the square root is chosen to make this expression. If q and a are both real, the above two equations are equivalent to this. So we'll want to compute this. See what happens. Okay. We'll say that a is equal to np dot sine r, and just a quick reminder that np dot sine, essentially, if it's a positive number, it returns 1. If it's 0, it returns 0. And if it's a negative number, it returns -1. That's all it does. Okay. So times np dot abs_r plus the expression r squared minus q cubed square root, and the entire thing is raised to the 1/3 power. Okay, where the positive square root is assumed. Next, compute this expression, and let's break it down. So it's saying that b is equal to q over a when a is not equal to 0, and b is equal to 0 when a is equal to 0. So another if statement, nested if statement. Okay, if excuse me, if a, and now I know that there's a much cleaner way to do this, but honestly I have not had enough practice to be confident enough to do it in a video. So we'll stick with what I know and what I'm comfortable with, which is, you know, basic if statement. So if b is equal to, if a is equal to 0, then b is equal to 0. Else b is equal to q over a. Okay. Makes sense to me. Done here. Or actually, we still want to stay in this else statement. So then return, actually roots is equal to, it's only one root, right? So a plus b minus a over lowercase a over 3. Return roots. And that should be the completion of the cube roots, the Cardano's method cube roots function. Well, at this moment in time, we have our cube roots function, which uses Cardano's method to find cube roots based on 3 coefficients, a, b, and c. And what we want to do is to write a Python function to calculate the specific volumes given pressure, time, for the SRK equation of state. Okay, and the way we're going to do this is we're going to be using the linear cube form of the cubic equation of state with z as our variable, z being compressibility factor, and we're going to use that, and we're going to use the function we just wrote to solve for those roots based on a pressure and a temperature, right? And you might be thinking, well, this equation is in terms of z, how are we going to, I thought we were going to do volume. Well, guess what? Z, the compressibility factor, is equal to pressure times volume over R times T. Guess what? We're plugging into this equation. Our knowns are pressure and temperature, right? And R is just a universal gas constant. So we can work in reverse and then get our volumes. So let's get right into this. So cubic excuse me. Cubic V, and we're asking for the inputs pressure and temperature, right? Oh, I always forget to define. There we go. Okay, and in order to utilize the cubic equation of state, what do we need? We need our constants a, b, e, and s, right? Guess what? We've written a function to take care of that for us. So, right here. So, cubic a, b, e, and s is equal to cubic a, b, e, s, and it wants a temperature. We wrote our function to want a temperature, right? Cubic a, b, e, s temperature, and it spits out our constants a, b, e, and s. Easy peasy. Okay? And what else are we going to do? Well, we said that we want to utilize the function we just wrote, cube roots, to make it return the roots of a function, right? And remember back then, a couple parts ago, we derived the linear form of the cubic equation of state where z is our variable, so z cubed some coefficient, z squared some coefficient, z some coefficient, and our constant some coefficient, right? We can use that now and put it into our cube roots. So cube roots a, b, and c, it wants 3 coefficients, right? And if we look over here, there's our coefficients a, b, and c. Let's get into this. The hardest part about this is just not making a mistake when writing everything down. Okay, so let's do this. So we'll want to return cube underscore roots. Okay, and let's do this one thing at a time. Our a, right? Apologies, I realize you can't see this. Our a is going to be this in the red, right? I'm going to keep looking down at this, okay? And just know that I'm not getting this out of nowhere. If you're confused about where I'm getting this, just go back. I think it's two or three videos, and I'll walk through exactly how we get these coefficients, okay? So it's a is equal to beta. Ooh, yes, beta, b. We define that as b. B times s plus e minus b minus 1. Okay? What's next? Well, let's divide it out by lines so that we don't get confused. Okay, next is our coefficient for z, right? This one's a little bit longer. E times sigma times beta squared. That quantity minus beta squared times sigma plus epsilon minus beta times sigma plus epsilon plus q times B, beta. Okay? Oh, that's right. That's right. Q. I was wondering, where did Q come from? I didn't find Q. I forgot that when deriving it. Oh, shoot. Shoot. Just realized that all of this is beta. Okay, we'll have to go back, okay? Small mistake. I forgot that when deriving this, we chose two expressions, beta and Q, to make our equation a little bit cleaner. So why don't we do that? We'll call this beta. Beta is equal to the correction factor B times P over R times T. And Q is equal to A over B times R times T. Okay, every time I said beta and I wrote down B, I meant beta. So, gotta go through and change all that. Okay? Beta, 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 and beta. Okay? Didn't miss anything. Great. And Q is now defined. We're good here. Okay. Time to take care of our last coefficient, C. Right? Which is the constant. And that is equivalent to negative epsilon times beta. Oh, sorry. Sigma times beta cubed. Okay? Minus epsilon times sigma times beta. We'll put that in parentheses just to be safe. Beta squared. Okay? Then minus q times beta squared. Okay? Oh, and let's make sure that our parentheses is closing. Oh, looks like it's getting confused here. It's getting confused. Okay. There we go. It's now closed. Okay. Okay. There you have it. Just in two functions, we've now written a Python function that, using Cardano's formula, calculates specific volumes given for a given pressure and temperature, and it's all based on the SRK equation of state. Okay? Wonderful.